Yeah, today we're going to talk more about the sides in right triangles, and we're going to talk about a couple right triangles that we call special right triangles because they have special relationships that exist between the lengths of their sides. Before we get there, we need to talk a little bit about square roots when they exist as fractions. And so if we have a square root in the denominator of a fraction, like we have here, what we need to do is called rationalize that. We don't like square roots in the denominator, so we want to get that out of there. And so what we can do is we can multiply both the top and the bottom of the fraction by whatever the denominator is. That's square root in the denominator. So I want to get rid of square root of 2 down here, so I'm going to multiply the top and the bottom by the square root of 2. That's okay mathematically. It's allowed because the square root of 2 divided by the square root of 2 is just 1. And multiplying anything by 1 keeps it the same. What we're doing here is just manipulating the way that this fraction looks. So we multiply both by the square root of 2. I'm allowed to multiply these two square roots together, so 2 times 3 gives me the square root of 6. And the square root of 2 times the square root of 2, whenever we multiply a square root by itself, we just get that number that's underneath the square root. So the radicand. So root 3 over root 2 becomes root 6 over 2, and that is the rationalized version of this fraction. So we can do the same thing with this one. We don't want that root 5 in the denominator, so we multiply the top and the bottom by root 5. Now that this doesn't have a radical over it, we can't multiply 5 times 5. What we do is we would just write them next to each other. That indicates multiplication. And root 5 times root 5 is just 5. And then sometimes we're able to just simplify a little bit further. We can cancel those two 5s. And the rationalized version of 5 over root 5 is just root 5. So sometimes when you rationalize, the fraction looks simpler. Like I think this one looks simpler because it's no longer a fraction. Sometimes it looks more complicated or maybe as complicated like this one over here. It's still a fraction. We still have square roots, but we want to eliminate the square root in the denominator. So let me do a couple more. Here I'm going to multiply by root 2 on both the top and the bottom and get 3 root 2 over 2. So maybe that one looks a little more complicated, but it's the way we want it. And then here we'll multiply by root 3. Again, because these things are both in square roots, they're allowed to be multiplied. So I get root 6 over 3. So crash course in rationalizing, that's going to come up in this lesson, and you need to be able to do it just like you need to be able to simplify a radical. So our first type of special right triangle is an isosceles right triangle. In an isosceles triangle, we have two sides that are the same length and two angles that are the same measure. So in this right triangle, I have one 45-degree angle. And because we know that all the angles add up to 90, we can determine that this other angle is 45 degrees. So I have a triangle here that's a right triangle, and it has two angles that are congruent, and therefore these two sides across from those angles are congruent. My two legs in an isosceles right triangle are congruent. They're the same length. Any triangle I draw that's a right triangle with two 45-degree angles is going to be similar to any other triangle I draw that's a right triangle with 45-degree angles. We know that's true because of the angle-angle theorem. If two angles in two triangles are congruent, we know those triangles are similar. So I can actually, we have what's called a reference triangle. The relationship between the legs in an isosceles right triangle is as such. The two legs are congruent. We'll call them a factor of 1. And using Pythagorean theorem, you can determine that the hypotenuse would be the square root of 2. We can get into that in class if you want me to prove that to you. So I have two similar right triangles here. They're not congruent. They're similar because they by angle-angle. And so I can write proportions. And so if I want to solve for x, I can write a ratio of the hypotenuse over the hypotenuse, x over root 2, and the side length that I know over its corresponding leg, 1. And now I just have a proportion to solve. This divided by 1 isn't necessary anymore because dividing by 1 just keeps something the same. And so to solve this, I multiply both sides by root 2. I can multiply that root 2 with this one and get root 4. Root 4 is just 2, and so I get 2 times 4, which is 8. So the hypotenuse here is 8. And in an isosceles right triangle, the legs are the same, so these two legs should be the same, so that means y should be 4 root 2 as well. So let's try another one. You should always draw the reference triangle, and I tend to draw the reference triangle in the same orientation as the triangle I'm trying to solve. So here I had it drawn in the same orientation, doing the same thing right here. The two legs should be the same, so when I'm done here, x and y should be equal to each other because they're both legs in an isosceles right triangle. So I can just solve for one of the variables. So I'm going to write this proportion. X corresponds with 1. 3 root 3 corresponds with root 2. That divided by 1 is kind of unnecessary now, but it's good to set us up. So I already actually know what x is equal to. But now we have this scenario where we need to rationalize our denominator because it's got a square root. So we'll multiply by root 2 on top and bottom. I'm going to get this 2 times the 3 is root 6. Root 2 times root 2 is just 2. There's my final answer for x. And so it's the same for y because they're both legs. So let me do one more of these. Again, I'm always going to draw the reference triangle in the same orientation here, so I can just match up corresponding sides in my two similar right triangles. The leg in this one is 4, and the other leg is y, and so those are supposed to be the same, so y should just be 4. Now I can write a proportion to solve for x, so the hypotenuse is x over root 2, and then I can write another fraction 4 over 1. And like I've been saying, that divided by 1 helps you set up the proportion, but then becomes kind of unnecessary. And so I can solve this by multiplying both sides by root 2, and I get x to be 4 root 2. I can't multiply the 4 in the root 2 unless I want a decimal, so I'm going to keep it this way as 4 root 2. The other type of special right triangle is what we call a 30, 60, 90 right triangle. So I have a right triangle and I know one of the other angles is either 30 or 60. I can use my triangle sum theorem to figure out the missing angle. So if one of them is 60, the missing angle is 30. And they also have a special relationship. In a 30, 60, 90 right triangle, the leg across from the 30-degree angle we have as a factor of 1. The leg across from the 60-degree angle is a factor of root 3. And so if you do some Pythagorean theorem, you'll figure out that the hypotenuse would be a factor of 2. So in another way, the hypotenuse is 2 times as long as the short side of the triangle. And the long leg of the triangle is root 3 times as long as the short leg of the triangle. It's best if you just sort of memorize the relationship here. So we can write two proportions to figure out the missing pieces. So let's write a ratio for A. A is related to this root 3. It's across from 60. And then my 6 root 5 is related to my hypotenuse. So I could cross multiply to solve this thing, but all I really need to do is multiply both sides by root 3. And when I do that, I get root 3 times 5, which is root 15. And then I'm going to simplify that 6 divided by 2 and make that 3. Do the same thing to find b. b over 1 is equal to 6 root 5 over 2. Just like with our isosceles right triangles, that divided by one thing doesn't really matter. Now we can just simplify dividing 6 by 2 to get 3 root 5. So it's important to always draw your reference triangle correctly. It's even more so when we have a 30, 60, 90 right triangle because all three sides are different and they're labeled specifically. The side across from 30 is always 1. The side across from 60 is always root 3. The hypotenuse is 2. So let's try another one. Again, I'm drawing my reference triangle, making sure that I have the angles in there the same way as the original triangle, and I'm labeling the sides correctly. So A goes with my hypotenuse 2, 10 goes with root 3. I can multiply both sides by 2 and get 20 over root 3. And then I'm going to rationalize. So I'm going to multiply the top and the bottom both by root 3 to get 20 root 3 over 3. Again, it might look more complicated than just 20 over root 3, but this is the convention. This is the way we're going to answer our problems. Could do the same thing for b. b over 1. Again, I'm going to get rid of that divided by 1. And the only thing I have to do to finish this is rationalize that denominator. I get 10 root 3 over 3. Let's do one last one. Again, being consistent, going to draw my reference triangle. Make sure I have the sides labeled appropriately. I can write the ratio u over root 3 and 4 over 2. Multiply both sides by root 3. And then simplify that 4 over 2 to be 2 to get 2 root 3. You could have done 4 divided by 2 at the start and then multiplied by root 3 and gotten the same answer. V is related to 1. Again, I can just get rid of that. So V is 2. And once you do a bunch of these, you might get really comfortable with the relationships between the side lengths, and you won't have to actually set up proportions. Like if you know the shorter leg is half as big as the hypotenuse, you can just figure out that the shorter leg is half of what 4 is, which is 2. But it's good that you can always get it right when you set up the proportions, and so it's good practice. I want you to try these two. I'll show you the answers. I won't go through them. If you have questions about them, make sure that you ask in class. So give these a try and then press play and I'll reveal the answers.